Silence came before light, not as a moment in time, but as a question science still cannot close, because the story most of us were taught begins with an explosion. Yet modern physics quietly admits that this explosion may not be the first page at all, and that single idea changes everything. What if the Big Bang was not the birth of the universe, but only a chapter in a much longer story, a story that stretches beyond what our equations can reach and beyond what our clocks can measure? For decades, the Big Bang has been described as the ultimate beginning, the point where space, time, and matter suddenly appeared. But today, many scientists agree on a surprising fact that rarely reaches the public. When we trace the universe backward, using our best theories, time itself becomes blurry, unstable, and undefined, meaning science cannot clearly point to a true starting moment. This is not science fiction, and it is not philosophy alone. It is the result of real mathematical limits, failed equations, and unanswered gaps inside the most successful models of cosmology. In this video, you will learn what the Big Bang actually explains, and what it does not, why the idea of a cosmic beginning is far more fragile than it sounds, and how modern theories suggest the universe may have existed in some form long before the hot expanding phase we call the Big Bang. You will discover why the word beginning might be the wrong word entirely, how time may not behave the way we expect at extreme scales, and why some scientists believe our universe could be part of a much older process that never truly started. This journey will take us through lesser-known ideas that challenge the classic picture, including models where the universe did not explode into existence, but transformed, rebounded, or evolved from an earlier state, leaving behind subtle clues that still echo through space today. Along the way, you will see why the famous image of a singularity, a point of infinite density, is no longer taken as a solid answer, and why many physicists now see it as a sign that our understanding breaks down, rather than a real event that happened. This video matters because it reveals how science actually works at its limits, not as a fixed set of truths, but as an evolving attempt to describe reality when reality refuses to be simple. By the end, you will understand why the Big Bang may be the beginning of our visible cosmic history, but not the beginning of existence itself, and why this distinction opens doors to deeper questions about time, reality, and the structure of the universe. Stay until the end, because the final idea connects all these threads into one unsettling possibility, that the universe does not need a starting gun, a first tick, or a first moment to exist at all. Welcome to our channel, a place where we explore the hidden edges of science and the questions that refuse to stay quiet. And if you enjoy deep ideas told clearly and without noise, subscribe now and join us as we look beyond the obvious and into the unknown. The Big Bang is often described as the moment everything began, but in science it is better understood as a model that explains how the early universe behaved, not how existence itself appeared. At its core, the Big Bang model describes a phase when the universe was extremely hot, dense, and rapidly expanding. It explains how space stretched, how energy cooled into matter, and how simple particles slowly formed the basic building blocks of everything we see today. When scientists talk about the Big Bang, they are not talking about an explosion in space, but an expansion of space itself, where distances between all points increased at the same time. As the universe expanded, it cooled, much like hot metal cooling when left in open air, and this cooling allowed particles to combine, first into simple nuclei and later into atoms. This process left behind clear fingerprints that can still be detected today, long after the universe grew vast and complex. One of the strongest pieces of evidence comes from a faint glow spread evenly across the entire sky, known as the cosmic microwave background radiation. This light is not coming from stars or galaxies, but from a time when the universe was young, hot, and filled with energy, before atoms even existed. It is the cooled remnant of early radiation, stretched by expansion into microwave wavelengths, and it carries tiny temperature differences that reveal how matter was distributed in the early universe. Alongside this glow, scientists also observe a precise pattern in the abundance of light elements like hydrogen and helium. The Big Bang model predicts these ratios with remarkable accuracy, showing how nuclear reactions unfolded in the first few minutes of cosmic time. time. The large-scale distribution of galaxies also supports the idea of early expansion, as galaxies are not randomly scattered, but arranged in vast filaments and clusters that trace the growth of small early density differences into massive structures. All of this evidence points to a universe that expanded and cooled from a hot, dense state, but none of it directly explains why that state existed in the first place. The model works incredibly well once the expansion is already underway, but it remains silent about what caused it or whether something existed before it. When scientists try to push the equations further back in time, closer to what is often called the beginning, the math begins to fail. Early versions of the Big Bang model suggested that if the universe is expanding today, then rewinding the clock would lead to a point of infinite density and infinite temperature known as a singularity. In this picture, space shrinks to zero size, time reaches a starting point, and the laws of physics collapse into infinity. For a long time, this singularity was treated as the true beginning of everything. Yet modern physics paints a very different picture. A singularity is not a physical object that science can describe or test. It is a sign that the equations being used no longer work. When infinities appear, it usually means the theory is incomplete. The same problem appears in other areas of physics, such as inside black holes, where density also seems to become infinite. Instead of accepting these infinities as real, physicists see them as warnings that a deeper theory is needed. Current theories of gravity and quantum mechanics cannot both operate fully at the same time under these extreme conditions. Gravity tries to compress everything, while quantum effects resist that compression, and the result is a breakdown in prediction. Because of this, many scientists no longer view the singularity as a true physical event. Rather than being the origin of space and time, it may simply mark the edge of what current models can describe. This shift in thinking removes the need for an absolute beginning at that point and opens the door to other possibilities that do not rely on infinities at all. One of the most important ideas that reshaped this discussion is cosmic inflation. Inflation proposes that before the universe entered the hot, dense phase described by the Big Bang model, it underwent a period of extremely rapid expansion. During this phase, space itself expanded far faster than it does today, smoothing out irregularities and setting the stage for the universe we observe. Inflation helps explain why the universe appears so uniform on large scales, why distant regions look similar despite being far apart, and why space appears nearly flat. In this view, the hot Big Bang was not the first moment of expansion, but the moment when inflation ended and energy was released into particles and radiation. This reframes the Big Bang as a transition rather than a birth. Instead of everything emerging from nothing, the universe moved from one physical state to another. Inflation does not answer all questions about what came before, but it clearly shows that the classic Big Bang picture is incomplete on its own. If inflation occurred, then something existed before the hot phase, governed by laws that may differ from those we observe today. This alone is enough to challenge the idea of the Big Bang as the absolute beginning. Once the idea of a pre-Big Bang phase is accepted, even more radical possibilities become scientifically reasonable. Some models suggest the universe may not have started at all, but instead moves through cycles of expansion and contraction. In these cyclic or big bounce models, the universe expands for a long time, slows down, and then contracts under gravity, eventually reaching a dense state where contraction stops and expansion begins again. Instead of a singularity, there is a bounce. This bounce avoids infinite density and allows time to continue smoothly through each cycle. In such a universe, the Big Bang is not the first event, but simply the most recent bounce. Evidence from earlier cycles might be faint or erased by each transition, but some effects could survive, subtly shaping the structure of the current universe. These models suggest that our universe could have inherited properties from a previous one, making cosmic history far deeper than a single expansion. Time in this framework has no clear beginning, only an ongoing sequence of changes, each linked to the last. Another approach that challenges the idea of a beginning comes from theories involving extra dimensions. In some versions of modern physics, the universe we experience is like a surface or layer within a higher dimensional space. In these models, what we call the Big Bang could be the result of an interaction between larger structures in higher dimensions. One such idea proposes that massive surfaces collided, releasing energy that appeared as a Big Bang within our universe. From this perspective, the event was not the creation of everything, but a local process within a much larger reality. These collisions could happen more than once, producing repeated Big Bang, like events without requiring a single origin point. Time and existence would extend beyond our observable universe, making the concept of a beginning dependent on perspective rather than absolute fact. Across all these ideas, a common theme appears. The Big Bang explains the evolution of the early universe extremely well, but it does not demand that the universe began there. Instead, it marks the earliest phase we can currently describe with confidence. Beyond that point, our theories lose clarity, not because nothing existed, but because the tools we use are incomplete. As physics continues to evolve, the boundary we call the beginning may shift further back, or disappear entirely, replaced by a picture of reality where time and space are part of a larger, continuous process. The universe in this view does not emerge suddenly from nothing, but changes form, guided by rules that science is still struggling to uncover. When the idea is raised that time may have existed before the Big Bang, the entire meaning of cosmic history begins to shift. Time is usually treated as something that started ticking at the moment the universe was born, like a clock switched on at zero. But if there was a physical state before the hot expanding phase, then time may not be limited to the story we can currently observe. In that case, the Big Bang becomes less like the start of the movie and more like the moment when the curtains opened and the visible scene began. Everything we can measure, from the motion of galaxies to the fading echo of early radiation, belongs to this visible chapter. Yet beyond it, there could be earlier chapters that left only indirect traces or no traces at all. This possibility forces science to accept a humbling truth. Our cosmic timeline may be incomplete, not because reality stops, but because our methods stop working. The deeper past may exist beyond the reach of direct observation, hidden behind physical conditions so extreme that current theories cannot pass through them. In this sense, the universe may have a prehistory just as rich and complex as the history we already study, shaped by processes we do not yet fully understand. At these extreme limits, where density is enormous and energy is compressed beyond familiar scales, physics itself becomes uncertain. The equations that work perfectly for stars, galaxies, and even black holes begin to contradict each other. Gravity demands one outcome, quantum effects demand another, and neither side fully wins. This breakdown does not mean nature becomes chaotic or undefined. It means the language science uses to describe nature is incomplete. A deeper framework is required, one that can unite gravity and quantum behavior into a single consistent picture. Until such a framework exists, the earliest moments or phases of the universe remain blurred. This is why many physicists are cautious when speaking about beginnings. They recognize that claiming a final answer at the edge of known physics risks confusing mathematical limits with physical reality. The Big Bang, in this light, marks the boundary of reliable description, not the boundary of existence itself. If time did not begin with the Big Bang, then the concept of before is no longer meaningless. Events could have occurred earlier, governed by rules that differ from those we observe today, yet still connected to our universe through continuity rather than creation. This reshapes the role of the Big Bang into that of a milestone. It is the point where the universe became transparent, structured, and accessible to observation. It is where cosmic history, as we can reconstruct it, truly begins. But the deeper question of why the universe exists, or whether it ever began at all, remains open. In this view, asking what came before the Big Bang is no longer dismissed as nonsense. It becomes a legitimate scientific question, one that demands better theories rather than simple answers. This shift in perspective explains why modern cosmology is filled with debate rather than certainty. There is no single accepted story of the ultimate origin, because evidence at these scales is subtle, indirect, and open to interpretation. Some scientists defend the standard picture, arguing that cosmic inflation combined with the Big Bang explains observations with remarkable success. From this standpoint, pushing beyond inflation may not be necessary until new data demands it. Inflation smooths the universe, explains its large-scale structure, and fits neatly within existing frameworks. Supporters of this view caution against adding speculative layers without experimental proof. They argue that while the singularity may signal a limit, it does not automatically mean a physical before exists in a meaningful sense. For them, the Big Bang remains the most practical starting point for scientific discussion. At the same time, other scientists actively explore models where time has no clear beginning at all. These researchers are not rejecting the Big Bang model, but reinterpreting it. They see it as one phase in a longer sequence, rather than a creation event. In their models, the universe may be eternal, in some form, evolving through states that recycle energy, geometry, or dimensions. Time, instead of starting, may stretch infinitely in both directions, with the Big Bang marking a transition rather than an origin. These ideas are not fringe guesses. They arise naturally when physicists try to remove infinities from equations and demand consistency between quantum theory and gravity. When infinities disappear, so often does the need for an absolute beginning. The debate is not about belief, but about which mathematical descriptions remain stable under extreme conditions. Each model carries strengths and weaknesses. Some explain observations well but rely on unknown mechanisms. Others are mathematically elegant but difficult to test. This tension drives progress rather than confusion. Competing ideas push scientists to refine predictions, search for subtle signals, and design experiments capable of probing the earliest accessible moments of the universe. Even disagreement becomes a tool, sharpening the boundaries between what is known and what is still possible. As this debate continues, the understanding of time itself becomes less rigid. Time may not be a universal background that exists independently of the universe. It may be a property that emerges from physical processes, gaining meaning only when change occurs. If that is true, then different phases of the universe could experience time in fundamentally different ways. Before the hot expansion, time may have flowed differently or been defined by variables unlike those we measure today. This idea dissolves the simplicity of a single cosmic clock and replaces it with a layered history, where time is shaped by the state of the universe rather than imposed upon it. Within this framework, the Big Bang is no longer asked to explain everything. It explains what it was designed to explain: the evolution of the early universe from a hot, dense state to the structured cosmos we observe. Demanding more from it may be a misunderstanding of its role. Just as biology does not explain the origin of chemistry, cosmology may not explain the ultimate origin of existence. Each layer builds on the one before, leaving deeper questions to deeper theories. This realization does not weaken science. It strengthens it by clarifying the boundaries of knowledge and guiding future exploration. The ongoing disagreement among scientists reflects the honesty of this process. No single voice claims final authority. Instead, evidence, mathematics, and observation slowly narrow the field. Some models will fail, others will evolve. New data may favor one idea over another or reveal an entirely new direction. Until then, the question of time before the Big Bang remains open, suspended between what is known and what is still being discovered. The universe, it seems, is not in a hurry to reveal its full story, and science, step by step, continues to listen. So the Big Bang stands not as the birth of everything, but as a powerful milestone in a much larger story. It marks the moment our universe became visible, structured, and measurable, not the moment reality itself switched on. Beyond that point, time fades, equations weaken, and deeper layers of existence remain hidden, waiting for better questions and better theories. What we call the beginning may simply be the edge of our understanding, not the edge of the universe. And that leaves us with one quiet, unsettling thought that science has not yet answered. If the universe did not begin with a bang, then what came before it? And how far does the story really go? If this journey into the deeper side of the cosmos sparked your curiosity, support the channel by liking the video, sharing it with others who love big questions, and subscribing for more explorations into the unknown.